Tonight we are happy to bring you American Pikas, Vulnerability, Resilience, and Conservation by Dr. Erik Beever. Erik Beever is a research ecologist at the Northern Rocky Mountain Science Center of the U.S. Geological Survey and is affiliate faculty at the Ecology Department at Montana State University. Erik has publications in diverse scientific journals and in diverse subdisciplines of biology. He's a member of the World Commission on Protected Areas, several other specialist groups, and numerous conservation/research societies. Erik has performed field research on plants, soils, insects, reptiles, amphibians, birds, fish, and small, medium, and large mammals, and in a range of ecosystems on the Western Hemisphere. He's interested in the questions at the nexus of basic and applied science, especially those that also inform management and conservation efforts for species, communities, and ecosystems. This evening, Erik will discuss mountains as natural laboratories, why Pika is a great role model to address innumerable questions, and provide high-level overview of lessons learned from across the Western North America. Please join me in welcoming Dr. Erik Beever.
I guess I might experiment a little bit with just no mic versus mic. Can you guys hear me without the mic, or would you prefer the mic?
Mic.
Prefer the mic? Okay, all right, good. So yeah, I'm going to argue in this talk that American pikas are both an indicator and a representation and a lens to view a lot of larger questions about what's happening in our mountains across the western U.S. That was a not so subliminal suggestion by a certain member of the audience right before the talk. So I give my props to that individual, who may or may not be 8 years old. So the roadmap for the presentation this afternoon is why should we care about mountains? Why are they good laboratories and I guess sources of knowledge? And then I'm going to really focus into these mechanisms, or how and why, these pathways by which climate change can affect species and communities. Again, this idea that the American pika is a model organism to address a lot of these bigger questions. And then talk about what pikas can tell us about mountains more generally. And then I'm going to start with the longest term data set that I have, which is 28 years from the Great Basin between the Rockies and Sierras. And then really dive mostly into work from a couple of my students, grad students, work in Idaho, Montana, and the greater Yellowstone ecosystem. And focus a little bit at the end about adaptive capacity and how species can cope with climate change. So, mountains really are important for several reasons. First of all, they constitute about 90% of the most strongly conserved areas in the West, in the country, in the continent, and across the world. So we're really putting a lot of our eggs of species and natural conservation in mountain ecosystems. Not exclusively, but a lot of, as a nation and the world, we're doing that. They have these, as you can see right out behind you and to the sides of you, they have these sharp gradients in both abiotic conditions, both temperature and moisture. And so that leads to communities being these sharp gradients in natural communities as well. So very low diversity at a place, but across that whole gradient, very high diversity. Key piece, often a flashpoint across the West, fresh water. They provide through that storage, I guess, the snowfall and then the subsequent melting of that snowfall provide fresh water for about 2/3 of the world's people. Very key piece there. A lot of us, over the decades and centuries, they've espoused a lot of aesthetic and recreational values, both consumptive and non-consumptive. However, because of their harshness, climatic harshness, and their isolation, they're generally, both the mountains themselves and the systems and ecological components within them are poorly instrumented and monitored. So you know you're a geeky biologist when you're listing things that are cool about a species, when you find out that something that is coprophagous is cool. For those who don't know, that means that they re-ingest their own feces, like all good lagomorphs. So why would they do that? What would be a benefit for them to re-ingest their feces? Yes?
Nutrients.
Yes, so this is reduce, reuse, recycle, so they're getting more nutrients out of this food the second time around. And in drier areas, they get the additional benefit of extracting more water. And I love trying to superimpose this behavior. Pikas have an apocrine gland on the side of their cheek, so they mark the edges of their territory by rubbing the edges of their cheek on the rocks. And I love trying to imagine humans doing that and what high schools would look like with that. So they have this broad repertoire of calls, these different functions of their calls. Everything from, and this is my northeastern accent, hey baby, how you doing? To, come here kid, hey, this is my spot, get out of here, scram. So, a lot of different functions, as well as predator alerting other pikas that predators are around. And unlike most species that live in the mountains, they're active year-round. So that really increases their energy, their energy need on that annual budget. A lot of species either migrate to summer range, a lot of the ungulates will do that, or they hibernate or estivate during the winter. What's also kind of uniquely interesting about them is they inhabit only talus and talus-like areas. So this is naturally patchy habitat that is really clearly distinguishable from the kind of the imagery that's available. And another interesting thing that leads to kind of a pretty non-branching family tree. For them, like their sister and mom and cousin all look very pretty. So you have a lot of local adaptation. So you have this radiation of different lineages, and the calls sound very different in the different spaces as well. And so some of the impetuses for our work over the decades, going back to the 1990s and even before that, in our work and other folks' work, we found that kind of back in the 70s, 60s, and 50s, the assumption was that these very remote, isolated areas, everything should be conserved within them. And now we're finding that that assumption is no longer, we can no longer make that assumption. Even if a place is very isolated, the effects of climate change can be pervasive. Really, most fundamentally, we're trying to identify patterns of vulnerability and resilience, trying to find out where wildlife more broadly are going to have problems and where are places that they're doing very, very well in. And what are those pathways by which they're having challenges or doing well. As was mentioned in the introduction, we really try hard to inform the management and conservation options. Our data were used, the first time that they were petitioned for listing under the Endangered Species Act, they used our data to make that decision to not list them. And mountain ecosystems are really, more broadly, frontiers for a lot of learning about systems. Why would they be a good model to understand what's going on in these mountains? They exist across really a third of the continent, everywhere from up in British Columbia and Alberta, down to New Mexico and California. They have this complete record over time where, with kind of glacial, interglacial cycles, their distribution has expanded and contracted. And a couple of researchers back in the 1960s put them in cages on top of the talus, and they died quite quickly. At the lower elevations and at the higher elevations they were fine, even though they had tons of water and tons of food. And they've been used for a ton of scientific, specifically ecological theory, everything from metapopulations to island biogeography theory to others. Practically speaking, what makes them really nice in terms of dollars per data point, low dollars per data point, they can be locally abundant in some places, unlike a lot of mammal species. So, trying to figure out what's going on with wolverines, it's a lot harder to get information from a lot of different individuals or links or things like that. Unlike things like voles and snowshoe hares, They have relatively stable population sizes. They're territorial, so these things can be often are pretty stable. And what's really nice and very different from most mammal species are nocturnal. Their job is to be secretive and hard to find. That means that you have to do a lot of times to have strong confidence that the species is not there. Not so with pikas. If they are in fact there, you have an over 90% chance of finding them if you're there at the right time of the day and year. So it makes it really nice. So what's also interesting and really different from not only all mammals, but really all animals, habitat, so they live in these rocky talus slopes, which really hasn't changed over time. And for those aware with kind of the endangered species literature, the biggest problem for most species is habitat loss and degradation. So last I checked, no one's putting condos on talus, surprisingly enough. So the other piece that's good, in a sense, is that trying to understand what's going on, we do have some change, so that gives us the ability to figure out why that's happening. So particularly for mountain-living species, there's a lot of particular pathways that we've looked at over the years. We've looked at food abundance or quality as potentially mediating changes across space and time. Habitat fragmentation in terms of rising temperatures, being able to change the connectivity of things. What we haven't looked at is diseases, pests, and parasites. That could be part of the equation, but really, really expensive and kind of local phenomenon, I believe. Competitors and predators, things like wood rats, marmots, and other things, as competitors. And predators, everybody and their brother likes to eat pikas, so they're part of this pretty expansive food web. We've also looked at a lot at physical conditions, everything from relative humidity, precipitation, temperatures at different seasons. So think about that. So unless you're Nietzsche, if you see the animal there, you know that it's there. Like Joanna here in the second part, once you hear them, or they're there. And recall back from earlier, I mentioned the hey, how you doing? Males are typically the ones that emit these long call, which sounds more like at the end they always have that fun little ending note, and then they have these active hay piles that they defend. And what's really, again, you're a geeky biologist when you think it's cool that they leave this really interesting poop. So they have this very unique fecal pellet. It's spherical, kind of looks like a peppercorn, and there are certain topics at the age when you have kids at the age of 6 that get brought up a lot. This is one of them. So initially they excrete a cecal pellet, and then they re-ingest that, and then they have these very unique spherical BBs or peppercorns. And then they also leave these hay piles that those in the drier parts of the landscape, those can stay around for decades, years to decades, depending on the place. So what's cool is then in a single visit you can tell not only where the species is now, but where it used to be. So then you can kind of get a look backwards into time. So this is just to give you a sense. I might move to this side to get it. Oh, there we go. That's better. Can you guys hear me just as well from this side? Okay, that's better. Let's get away from that feedback. Still working, right? Okay. This is some of the areas that we've worked across the West since 2012. This again is where we're going to start here in the Great Basin, and we're going to spend time here and both of these areas here in the talk. But we've also worked in New Mexico, southwestern Utah, and some in the Sierras and the Columbia River Gorge. Some of the tools that we use for our research, we've used repeat photography, so giving you perspectives on things like tree line, legacies of different land uses, productivity through time, and as well as conifer encroachment in parts of the landscape. We also use these, which they still blow my mind, these microclimate sensors. They're about the volume of 3 dimes stacked on top of each other. And now, I think their capacity is increased by 32-fold relative to when I started using them. So you can leave them out there for 8 years, taking temperature measurements every hour, and you can pick them up, and those data will be there for you, which is kind of a neat thing. We also look at field notes, and I just have to give you one quick side trip for a funny anecdote. There was Charles Pearson in 1947. He was bemoaning the fact that they were putting up, in his words, putting up all these specimens, which means shooting all these animals. This is because they were essentially describing what animals are out there. It's kind of like I guess a survey, just trying an inventory of what is out there in our public lands. And he was bemoaning that we have to put up all these specimens. In 1947, he was saying, I think we should instead be really understanding better the physiology of these water shrews and how can they do this. And he was really quite frustrated. And he ended up writing in Spanish so that his supervisor couldn't read what he was saying. He wrote in Spanish all this claptrap about how important it is to put up specimens. Then the very next day in his notes, he writes, "Today I am a yes man for science." And he crossed out the lowercase s and put a capital S. I think he had a talking to by his boss. And I am putting up N+1 specimens to advance science. It's just so funny. Some of the things that you get back from these folks from even a century and a half ago. Really fun. So just want to give you a sense of what these sensors that we put down in those places that pikas live or had lived. So here's a place, here's a site. Each of these different colors in this one is a different sensor. And you can see this is a place at which pikas are now gone from. And these two the two lines across are temperatures at which pikas, when they were kept in cages, died from overheating. You can see here that across even 1 year, there's a ton of days that temperatures down in those talus interstices where they live, they were way above that. And also note that the temperatures, ironically, in those same super hot places in the summer, get super cold in the winter. Why would that be?
Cover.
What kind of cover?
Snow.
Exactly. So as a function of, these sites are also, many of these high elevations across the west get really darn cold in the winter, and there's no insulative blanket of snow. They get down to minus 25 Celsius, even in central Nevada. In this case, we have sensors across the west. Yeah. So this is kind of cool. I will refrain from political commentary, but it's because of a use of atomic bombs. We have two sides of the bomb curve where a particular level of carbon-14 can be at. So you find out the level of carbon-14, and that means that you get 2 years or two ranges of dates that most samples can be at. You can see, however, in some cases there's just one. This is from Adel, Oregon, southeastern Oregon. Pikas were last there. This is radiocarbon dating their fecal pellets. So they were last there between 1668 and 1945. This one, which was in the Sierras, was between 1453 and 1625. Super interesting. And then some of them are very modern. So they were potentially there as recently as 2009. So another neat tool to have in the toolbox. So as I promised, we're going to start out in the Great Basin. We have this really cool historic work from 1898 to 1956. So I went back and resurveyed those sites. And then in the 90s, 2000s, 2010s, and then into the 2020s. And those sites kind of span all across the region here. The ones with stars are the places where the species has been lost from across that entire 2-mile radius. All of the talus, they're gone from all that talus. The circles are where they remain. The yellow squares are places where that we have either archaeological or prehistorical or paleontological evidence of them. And I think that's it. Yeah. Okay. So what are we seeing? What are the kinds of things that we're seeing? Well, first of all, of those 25 original sites, 6 of them had experienced site-wide loss, like they were gone from the entire site, which translates to about 5,300 NFL football fields with end zones between that first period, 1898 to 1956. Between then and the 1990s, which was about 60 years on average. Between 1999 and 2008, 4 more sites were the pikas were totally lost from, which was about 1 site every 2.2 years. And then this is the embarrassing part of the talk. From 2008 to 2020, there were no additional extirpations, so site-wide extinctions among those original 25 sites, but 6 of 10 quote-unquote new sites did not have pikas still. And it's embarrassing because I say new, but it was in a 1924 publication. So not that new of a publication, I just wasn't aware of it. So a colleague sent me that. So this, at about 46% of the sites, there are no pikas within that 2-mile radius, or 3 kilometers specifically. And so if you look at kind of the percent of those sites out of the 25 originally that have had site-wide loss, it's kind of gone up through time. That's one thing that we're seeing. Another thing that we're seeing is upslope migrations. So what's happening, even as early as in this region, and in farther the southern parts of their range, even in 1898, they existed to the top of the mountain peaks there, and what we're seeing is kind of a concatenation from the bottom up of where they are living. That pace of retraction upslope averaged about 13 meters per decade from the historic regions through the 1990s, and during that 1999 to 2008, it averaged about 145 meters per decade. So keep in mind that there was a lot of drought years in that time space there. Since then, it's averaged about 50 meters per decade retraction across. This is across a 100 million acre region. So on average, that's what that average looked like. A couple of global meta-analyses of species that live in mountains. One in 2003 found 6.1 meters per decade moving upslope, and 12.2 meters per decade in 8 years later, a reanalysis. What's interesting is that in most of these sites, there's not any change in the maximum elevation, in the average elevation, or the median elevation. So what we're also seeing is we put out these sensors at about 330 locations across this region, which is kind of like finding a needle in a haystack. So we have a lot of different tools to refine those specific locations. So what we have is at the places that didn't become extirpated site-wide, we had about 164 sensors out. From 2013 to 2017, at sites that were originally occupied that changed to unoccupied, there were 35 instances of that at 14 different sites. That was about 21% of the remaining sensors. And then an additional 5 more did that from 2017 to 2019. And the opposite way, going from unoccupied to being occupied again, that happened at 8 sensors at 4 sites. So this cool on again, off again pattern. The problem is that we're seeing a lot more going off than going back on. And a lot of these ones that became reoccupied were recovery of places where a site had almost crashed. And so in this region there are wild horses and a lot of really unique, as here as well, a lot of really unique local conditions that really make a place a place. Okay, thinking caps on. I'm going to show you 4 pictures of areas in this region where the species remains at. Then I'm going to show you 4 pictures of where they've been lost from, and I want you to kind of propose to me what you think is going on here. Okay, here's one of the first ones where they are. This is in northeastern Nevada. Hello?
Is that near Wells?
That is pretty close to the Wells, yeah. Yeah, this is in the Ruby Mountains.
Moy Canyon?
Lamoille Canyon, yes, it is. That's right, yes. The Grand Master, all right. Touche. Okay, this is in the Sierra Nevada Swagger Canyon in the Sweetwater Mountains. This is right near Wells, East Humboldt Range, which you can actually almost, well, if you had really great vision like eagles do, you could actually see this from the highway. So those were the four that Pikas remain at, and here are one more. This is actually almost the same picture as was taken in a 1934 picture, Long Canyon in the Ruby Mountains. And here are the four pictures that they're gone from. This is in 4 miles southwest of McDonald Peak in northeastern California. This is in the White Mountains at the California-Nevada border. And these, a lot of the answer also resides in this region, so I'm counting you guys to get this. No pressure though. This is in the central Nevada, the Toyabe Range. And this is the Monitor Range in Green Monster Canyon and Monitor Range. An entire subspecies was described from an animal that was taken here. So what do you think? What is the difference between those first and last four? Any thoughts? Overarchingly, differences. Okay, so vegetation, drought. Okay, look at the colors in this here. Yeah, moisture. That's it. That's all those things are kind of so that's very, very. A lot of these species in these last four are in the more arid parts of the landscape around here as well. So you have a lot of pinyon and juniper. You have mountain mahogany, and this much deeper green in those first four. So when we looked at density in surveys in the 2000s, the greener it was, the greener that vegetation was, the more pikas that were out there. I keep pushing the wrong part of the clicker. Okay, so what's kind of interesting, and I would say to me really unsettling, is that the rules are changing over time. So even in less than a decade of difference of time, the factors that using the same models, the same sites, and comparing what's the strength of evidence in terms of different hypotheses, what's striking first is that, kind of going back to my days as a kid with Sesame Street, there was do you remember that cartoon that, duh, plants need water, man? That was a little cartoon when I was a kid. And kind of wildlife biologists would say, duh, animals need habitat, man. So, ironically, this species is really weird because the amount of habitat, number of home ranges that we counted on the ground, how much pika habitable talus habitat is there, that had almost no ability to predict how many animals we detected. So that assumption of kind of animals being well correlated with their habitat is we're breaking that assumption now. We have this additional layer of suitability of climate that needs to come into the picture. I guess the unsettling piece for me is that what happened in the 1990s, like the factors that govern those patterns of abundance across this region, was almost as much change as possible. Like almost the maximum amount of difference between the two periods that was possible. So it's unsettling because you tell a wildlife manager, or you tell a land manager, well, this is what's going on, but less than 10 years later, those rules are totally broken. So that's one thing that can happen. What we've also asked is, are the rules changing over space? And this came from talking to land and wildlife managers, go up to British Columbia and Alberta, and then trying to talk to people down in New Mexico or Wyoming or Idaho, and they say, what do you guys think is going on here? And to the assumption that scientists have used for the last couple of decades is that the same factor is limiting species across their whole range. And we had all these managers saying, yeah, I call baloney on that. Like, that makes no sense to me. And so I said, well, let's try to test that. And so we're interested in trying to be really thoughtful about what the species biology is and have that inform how we look at this. We wanted to look at it through several different analytical frameworks to corroborate what we're finding and have it be very hypothesis based. Like, okay, is this a function of lack of snow? You know, having cold stress in the winter? Is this a function of lack of vegetation? Is this a function of just maximum temperatures are too high in the summer? Or is it kind of more of a slow burn? All of those things. But most fundamentally, we want to say, how can we inform what's happening at these local management relevant scales? And I don't know if you can see this, but it kind of looks like a palette, a rainbow palette. And what's interesting is in this driest part of their range, summer precipitation is most strongly governing the patterns of where they are and are not. Down in the southern end, where it's the hottest part, funny enough, summer temperature is pretty much the strongest governing factor. Up in the northern part of the U.S., winter temperatures and winter precipitation. If you go into the Uintas, it's all about winter precipitation. Yeah, and so, where are we here? So here in this part of some parts of it here are in summer precipitation and summer temperatures. So very empowering for a local manager that we have these 5 different pathways that people can look at to see what's going on. And it's not necessarily giving you the final answer, but at least you can focus down on what things can you think about the test. Some of our recent work across this region, we have some work in the Sawtooth area, as well as in the Absaroka Beartooths, Bitterroots, and the Steens Mountains. This was explicitly to look across a gradient of precipitation and what's going on. So you probably can't read these specific ones, but in this study, across 200 sites, both with and without these microclimate sensors, water deficit was a big predictor, as were temperatures during the winter, and then the greenness of the vegetation was also a strong one as well. This one's really cool. It smacks a little bit of Big Brother for me. It kind of scary. I had a colleague who can be described as nothing but a savant. He made a system to put physical cameras on the belly of a plane, and he would have like a glass bottom to that plane, and he would take pictures at like 60 frames per second, and he would take pictures of true color infrared, and then thermal infrared, which was absolute temperatures. And he was from the Northeast, so he was not used to the plane going all over the place like we get thermals and stuff out here. So he lost a lot of weight. I'll just put it that way. And we had to get like all the data in like the span of 3 hours on the last day because he was going back. He was used to like what made me salivate when I saw this guy talk first. He like says, "Well, yeah, we were going out doing these moose surveys out in New Hampshire, and we saw these." And he had actually the first one was a slide of like these heat sources. And then, like, we saw these 6 moose out there, and he says, but then, and he said, from the same exact location at the same time, we have this color imagery. We can see that there's 4 moose, 1 deer, and a coyote. And I was like, oh my goodness, this is great. So what we're doing with these data are to try to create this very high resolution imagery to be able to fly a plane over an area and say, well, here are some places that we've never surveyed that might be most promising to have pikas and that we can survey into the future. Because it's a big world out there and we've only scratched the surface. So another student's work has, and it's really visible across this region, that you all are super fortunate to live here. This is a really amazingly gorgeous place. Neat space. Uses this, I guess the truism that, especially with tall mountains, you have, as you move up in elevation, the temperatures go down, and on that windward side of the mountain, you have a lot more of the precipitation that's dropped than on the rain shadow side on that drier, often eastern side. So what this student did is to look at whether the pikas were there or not in each of these patches. What was the density of them? How many animals per area? And then how far had their distribution moved upslope in each of these 64 watersheds. So he did this work across spanning the Continental Divide, in the Beaver Heads, the Lemmis, Italian Peaks, and the Tobacco Root Mountains in Montana. In each of those 4 mountain ranges, he established transects going up and over the peak of the range in 8 different transects for each of those 4 mountain ranges. And then he essentially surveyed each patch. Did we have no evidence at all of pikas in the red? Did we have that they used to be there? We can see those old hay piles or old pellets. Or are they currently there in the green? And so what we found is that they had retracted upslope about 280 meters, about 850 to 900 feet in elevation, as indicated by those old evidences. But one watershed they were totally gone from the whole watershed, and some watersheds had experienced no retraction at all. Their distribution was exactly what it was historically. Just a couple of graphs to show you just some of the differences in the individual ranges. In the Beaver heads, we had a lot of almost all the sites that had a higher number of days above 26 degrees Celsius. Most of those had pikas lost from those. The Italian peaks didn't have any sites that were that hot, and the tobacco roots didn't have as many. The Lemhis actually had a good number of sites that got quite hot but still had pikas in them. And as you move in each of these 4 mountain ranges, as you move farther towards the larger patches, this is the size of the patch. This corner of each graph is kind of the best. So like biggest patch, coolest in the winter. Coolest in the summer. This is just a kind of all the different factors that we looked at, what the individual strength of their relationship was to both abundance and occupancy. I will spare you get into the specifics there. But in kind of more broadly speaking, the things that affected abundance were mostly a function of temperature. And it turns out in abundance, so that was actually more strongly governed by factors that were operating in winter. And I think again through probably through snowpack was what was mediating that. Whether the site was occupied or not, had both ecologically available water, size of the home range, and temperature in terms of whether the site was occupied or not. And then how far upslope their distribution had moved in each watershed. And that was actually a new approach. Folks hadn't looked at watershed-wide retraction. That was strongly a function of temperature, and then secondarily precipitation. Abundance was mostly a function of winter dynamics, but the other ones, occupancy, how far that distribution had moved upslope, were summertime factors. These are kind of cool. These actually allow you to see things, the relationships, very visually. So at lower temperatures during summer, average temperature across the entire summer period, the lower the temperature was, the more likely it was to be black, which is currently occupied by pikas. So I'm not sure what happened at the very lowest temperatures, but actually what it is, at the very summits of a lot of these mountain ranges here, you had taluses that weren't as deep, so like and a lot of the snow would get blown off at the very, very summit of the mountain. So that actually had a little bit less likelihood, but the higher and higher it was during summer temperatures, the less likely it was to have pikas at them. The more summer precipitation you had, the better it was for pikas. The more frequently that you had days above 26 degrees Celsius, the less likely you were to have pikas. The more moisture deficit you had, less likely to have pikas. And the drier it was in the summer, the less likely you were to have pikas. And I wanted to give you a little bit of another, also the greater Yellowstone ecoregion perspective, what we found there. So when we think about what constitutes refugia or refuges for species and populations across long time periods, those can vary by both time scales of like glacial, interglacial time scales, as well as spatially. In some places, like in this region and others, you have some of these kind of little caves and things like that. Some places have ice in those caves. Moss in some regions can be a big, you can see like it'll go up to 90 degrees Fahrenheit during the day, and under the moss, it doesn't even change at all. It's like a flat line. It's kind of amazing. And you can see here, this is actually right around from here. Zach Holden did a study. He characterized with a ton of different little sensors across the region. Temperatures at different parts of the valleys and ridges get different temperatures. This is from Grand Teton National Park. You can see one area has a lot of snow being retained from some of these moraines out there. Deep canyons can be big refugia as well. North-facing slopes, as you know. So for this study across the GYE, we had 4 different places we worked at. Grand Teton, Custer-Gallatin National Forest, Yellowstone, and Red Rock Lakes Refuge. And the different colors here, blue being Grand Teton, the green being Yellowstone, red the Custer-Gallatin, and here's Red Rock Lakes. And so what I wanted to show you, we had like in the 2010s, so 2014 to 16, and then 2019 to 2021. In Grand Teton, they were almost at 100%. This is Pikas' happy place across the U.S. They get a ton of snow. Custer-Gallatin had a lot more extirpations than recolonizations at 18 versus 7. Yellowstone was about the same in terms of occupancy, but their abundance went down really dramatically. And Red Rock Lakes had one more recolonization, so they're actually their percent occupancy went up quite a bit. And then GYE wide, we had about, like I mentioned before, we had about twice as many of them had lost pikas as patches that went from unoccupied to occupied. So those numbers are really quite high compared to a lot of other places where the percent losses have been much higher. Between 2012 and 2014, Zion National Park had the species totally lost from it. And so it kind of is, I guess, a concrete, specific example of how these things are not just abstract. These are happening in some cases in very real time. And these data are actually not published yet, but in New Mexico, we're seeing quite a bit of change in their distributions. What I wanted to show you is across this region, the number of days below 0C, which I think this is using gridded climate data, so not using sensors that's really specific to that location, but using kind of estimated conditions. The larger the number of days below 0C, which I think is a proxy for how long that snow cover is on. The longer that you have the snow cover, the more likely it is to be pika occupied. And then the drier it is in summer, the less likely you are to have pikas there. And then I would just want to summarize the abundance data. In Gallatin National Forest, Custer-Gallatin, between the 2 periods, the abundance went up quite a bit. So apparently a rise in abundance between the 2 periods. Grand Teton was about the same, about an 8% decline in abundance between the 2 periods. Definitely not significant. Ironically though, as I mentioned before, Yellowstone declined abundance by about 40 to 50%. Really dramatic loss. A really cool piece that I'm pretty sure is happening, well I know is happening here, from my students have been telling me that these natural locations of things like rock piles or trees falling onto talus, or even dead and down trees, snags, those are being places where pikas are hanging out. So they're exhibiting this flexibility in this region in areas like this. And what's really unique or interesting to me is another study from 2016 predicted pikas to decline really strongly across this century in Yellowstone, and whereas they were going to stay at a nearly 100% occupancy in Grand Teton, this is very, very reminiscent of what we found in the course of like 6 years. We saw declines in Yellowstone, a happy place in Grand Teton. So that's kind of cool that we have corroboration across the 2 studies. So what we learned in this GYE study, this is a very cost-effective indicator for a lot of questions that are applied. Across this region, across the greater Yellowstone, they have really high levels of occupancy, slight apparent declines in a couple of the regions, and a pretty marked increase in abundance at the places within Custer-Gallatin that they remained at. this stays below 0C, which I think is related to snow cover, was important. And a little fun fact, the earlier study said that pikas never really existed in the Yellowstone River, and we actually went out there and did a much more comprehensive survey, and they used to be all throughout the Yellowstone River. So a little bit different interpretation there. Minor, but important, because it shows that things are changing there. In this region, vegetation is not limiting, and we, because of this minor little detail about grizzly bears and not wanting to be out at like 9:30 at night, we sampled during the middle of the day, which we don't do anywhere else outside of grizzly country. It improved our models to include what the temperature, the time of day that you surveyed at, but not enough to be a huge difference. So in this region, that works out okay to do that. And then more for the entire talk, each species really responds individualistically, so we can't necessarily extrapolate these results to all species. And I think it's really critical to think about how and why species can or cannot cope. And species responses can vary across space and time. So with that, I'd like to thank some individuals who've come to support me. And thank you all for your time and attention. And all these folks here for funding and field assistance and for critical input and assistance, as well as those who have come before me for blazing the trail. Thanks. I'd love to take questions if anyone has any. Yes?
With climate change and the hotter forest fires we're having, I realize that pikas are in the rocks, but as hot as it gets in the area, what's the impact on it?
Specifically of the temperatures or the fires?
Fires, well, both.
Both. Okay, yeah. Excellent question. Funny enough, just came back, not yesterday, but the day before, the 2 nights ago, from the Dixie Fire, a million-acre fire in northeastern California. And we've obviously had fires across the West in this country, even here, for centuries to millennia. The difference is that we're getting now these really catastrophically big, high-intensity fires. A function of a lot of things, but that's a very insightful question, because what we found there, ironically, as I don't know if you kind of got that theme that hotter and drier is generally bad for pikas, and it's a lot of different ways, but it's kind of most fundamentally it's a 1-2 punch. It's both more physiologically stressful for pikas to remain, but I didn't mention this, is that it's also harder for them to move back in hotter and drier. They don't disperse as far in those hotter and drier places. So interestingly, in that Lassen area of the northern southern Cascades, northern Sierra Nevada, it turns out that the area that was burned was in the cooler, snowier, rainier part of that region. So there was some loss. There was like 15% loss of patches no longer had pikas relative to what we had our data from 8 to 10 years before. But that was very minor compared to where we sampled outside of the fire. No fire at all. In that hottest, driest part of that region, we had a 53% loss. So I think that those kind of the northeastern, kind of tending into the Great Basin sagebrush part of that forest, I think they were kind of at the edge. So another fire, and as I mentioned, there's a lot of context dependence of what fire might look like, or a lot of these things. Whereas in glacier, cold stress is a big deal. In New Mexico, the heat. So to get to your question about the general importance of temperature, the most common factor that's been governing them, their distribution, is summer-long temperature. So what's ironic is that nighttime and minimum temperatures are actually rising a lot faster than maximum temperatures are. I don't feel that as much, but what occurred to me recently when I juxtaposed a trip to Grand Teton with one to the Great Basin is, when I started in 1994 out in the Great Basin, in the places where pikas are no longer at, I was getting up and it being 20 degrees in the morning, and now, you know, at 4 in the morning, and now, even at the places where pikas remain, I never use a rainfly. It's that warm, overnight. So, excellent question. Both of those things happen, and talus is a refugium. If the patch is big enough, you can have a kind of a rocky interior that they can retreat to. So, great question. Yes.
Thank you.
Yes.
How do they move to a new site? Is it some young, intrepid little explorer pika who just jumps away in the night, or is it a slow progression, or what's that process? What's that life cycle process?
Well, I'm going to get out my knitting needles and tell you what I think. We don't really know.
Okay.
It's an excellent question, and what I wanted to do was to put out like a, you know, they put pit tags in fish. Wanted to put pit tags in pikas to see when are they leaving. I think the challenge is, I think it may be depending on where you are in the range when that happens. So what's kind of interesting, again, these places that are hotter and drier, they're not I mean, understand this, that like, so the cheetah is kind of like the classic example of an unbranching family tree, like very, very low diversity, genetic diversity. A lot of pika populations are lower than cheetahs. So they really are, like, all their relatives look hot to them. So, I guess in New Mexico, we actually went out in June, and to this one site in Bandelier National Monument, and it's kind of a little bit of a challenge for me, because there's, in that monument right now, as of June 2021, there were 4 animals left. So what do you, in 2 patches, so what do you recommend to that manager? But they're actually, it's really neat there, because they are really excited about trying out some experiments to create, as I mentioned, those little natural refugia, to create things to put trees over talus slopes, things that I've observed over the last 30 years. But someone went back in July, and I went there 4 times just to make sure this one patch, like, they're not there. I'm not positive, but just to make sure, triply, quadruply sure they were not there. Next month, in July, so in that case, they moved between June and July to that patch. We think that a lot of those happen in like late fall to winter, but it's kind of it's a great mystery. So, excellent question. And I think in some cases, what we do have through some genetic work in North Cascades National Park, this idea that, as I've kind of portrayed to you, that pikas are kind of marching up slope. What's interesting is that they had genetic data there, so they had individuals marked from each of these different elevations and a couple of different transects. What's actually happening is you have a ton of pikas being produced at the very highest elevations, and it gets too densely packed, and all the juveniles get kicked out, like, scram, get out of here. So then they all actually go downslope, and then in these lowest elevation sites, they just kind of choke out, and it's like a sink, what's called a sink. There's really there's no reproduction there, they can't even survive there, they just keep getting recolonized, they're moving downslope. Yeah, great question. Yes?
How do pikas keep warm in the winter? How do they survive?
Excellent question. How do pikas keep warm in the winter? 2 things. They have a really high engine. They just keep eating, like my friend who's an Italian, like an Italian mother, like, keep eating, keep eating. so they have high metabolic engine. So they keep eating. What they do is they create these hay piles. And what's interesting is that some researchers removed hay from those, and they actually didn't see a greater mortality. More animals didn't die. But another study found the opposite. When they did remove hay, they did greater death. So that they provide this essentially this insurance policy for a winter by creating that hay pile. So they continue to eat off of that, and they also that hay pile also serves as a physical insulation. And then they live under the talus. And you look at those sensors, it's a flat line. It stays right at 32 degrees Fahrenheit. So they also have, which is bad for heat, but good for cold, super bomber, awesome insulative hair. So there's very, very little heat is emitted from them. So they're really well insulated as well. So all of those things, they, yeah, great question. Yeah. Yes.
Well, I'm interested in density differences with the different patches, but first I want to know, how do you count pikas?
Yeah.
What are your methods? Are you trapping them, or what do you do?
No. Excellent question. So, there are quite a number of ways to look at density, or to I guess, quantify density. We because of the fact, the more elegant and eloquent ways look at distance sampling. So how far are pikas being detected off of the line that you're walking? What we do essentially is we walk the make elevational contours across that patch. If we haven't found pikas at all, we go really densely packed to make sure that we're not missing them at all. But once we have pikas there, then we can say, okay, they're there. What's that density? We don't want to walk over the same area twice. And then so what we do is we count the number of individuals that we've detected. And they're again, because they don't move very much on any given day, you can kind of tell where that call comes from. With the caveat that even in the early 20th century, they were called the great ventriloquists. So they're pretty good at throwing their voice, so to speak. And then we count up the number of times that we find either a hay pile, a fresh hay pile, a sighting, or a call, and then we divide that by how much how many transects we've walked, how much survey effort. And so I will say that in most of our study regions, we're not as able to explain the factors that are governing density. It's a lot harder to nail that down. So I kind of think about density as habitat quality, whereas occupancy is the habitat suitable at all. So it's a little bit more nuanced, and like individuals to remain nameless that may have declines in their hearing, that can be a factor. You know, how well you can see, and then do people miss the hay pile? So I kind of create this ambiance of fun when we do double surveys to quantify that detectability. A little bit of a fun little friendly competition to see like who's going to miss the most evidences, like hay piles and that, just to kind of keep everybody keenly interested in detecting things. But like the one study, we had that one student worked in the Sawtooth specifically. He had 2 individuals surveying 41 different patches out of the 200, and out of all 41 times they got the same, whether it was occupied or not every single time. So 100% detectability. So then you have the question of, is the species detectable or not? Then you have, are individuals detectable? So, and that went from like 85, are individuals detectable, went from 85 to like 98%. So again, not a good mammal in that sense. That's really, really high for mammals. Yeah, excellent question. Did that answer?
Thank you.
Yeah. Yeah. So do some other folks that like survey in one canyon of one mountain range, they will trap animals and look at individual like fecundity, so how many babies are they producing, what's the parasite load, and things like that. I've kind of gone the approach of thinking about landscapes and saying what's happening broadly across this region. What can we learn? What can I tell managers what's happening across this region versus in this 1 square acre? Just different. They're complementary approaches, but that's kind of the way I think about science often. Yes.
Could you give an example of what you do tell a manager? Would you maybe give a condition you found and what you prescribe?
Yeah.
Just curious how that works.
Great question. So, I think part of why I've gone to doing that is I feel like kind of the paralysis and defeatism that can kind of come with climate change is kind of I don't think that's necessarily the only approach. And so in regions where I guess patch size is really important, let me be real specific. In the Columbia River Gorge, this is a continentally unique area. Like pikas exist there down to sea level, and I guess in that region you have south-facing Washington and then north-facing Oregon, and the north-facing Oregon is almost all federal land, and so there, these folks have it's mostly all Forest Service, so they have all these agency mandates and I guess goals that they're trying to achieve there. Other side has a crazily diverse patchwork of different jurisdictions. So a lot of those are county lands, a lot of those are private lands, and so a couple of things there. Moss is really important for keeping that climate in the local area really, really constant. So they have asked about are there places where we might want to restrict climbing? So essentially not removing the moss, like rogue trails, specifically where folks are just kind of going up trails off the trail. And I said, well, there's a couple of examples where we have, not like an entire 50 patches, but a couple where I've seen the moss cover go way down and the number of pikas go way down. So not hard and fast for sure, but it sure seems like visually evident, that piece. So conserving moss there is a big deal. They had a fire, the Eagle Creek fire in 2017. So they took a sharp hit, pikas did there, but in that central heart of the Cascades, they're recovering quite well. Another piece that I talked to both the county folks and the state DNR and state wildlife, the Department of Fish and Wildlife there in Washington, is the county wanted to take talus for road construction. And so, I had a couple of the sites where like, wait, where's the site? There's no rocks left. Whereas the state was like, this is truly a continentally unique location here, and so this is one of those hard questions too. Like, we know very clearly, like for example, like if you cut down certain amount of trees, you see what's called edge effects of different, like different species are affected at different distances from that edge of that forest. What we don't know, which is the same as in the gorge, is how many patch cuts does it take across a landscape until you start losing wolverines or start losing lynx? Those cumulative, bigger scale things are harder questions. And so I said, I guess just be cognizant of, it's not permitting in any one thing. It's kind of the whole collective is where, because you're essentially breaking links, and so in that place I think the links are pretty important. The mini links rather than animal links are important to keeping them around. So there's a couple of examples specifically where I've helped weigh in, and also I've been proposing for a few years these natural experiments to get, because part of our challenge is everything is observation, and we have these correlations that we have a lot of repeat studies that suggest that these things are going on in terms of the mechanisms, but if you manipulate things in a positive way, that then gives managers a tool. So using snow fences, putting trees that have been cut, putting those on, and these are all from things that I've seen, from natural phenomena that I've seen out in the wild. So that's where that's coming from. Yeah, excellent question. Thanks. Yes?
Will you explain a little bit about how the hay piles compost and transition from being toxic to healthy kind of thing?
Excellent question. Yeah, this may sound like a knitting needle story, but there's been actually a lot of research into the chemistry of hay piles. So again, remember that this is what they go out and they're like these little busybodies doing up to like hundreds and hundreds of trips each day. They're very selective what they put in their hay pile versus what they eat immediately. If you look at the chemistry of what they eat immediately, it's very different from what they put in their hay pile. Also, what they eat out of their hay pile first has different chemistry from what remains in their hay pile, so that's pretty cool. They also have used species that are anti-mildew, anti-mold agents that they put in there, which is kind of blows my mind. And so, again, these are these insurance agents. This is insurance to be able to survive that long winter. Places like the Columbia River Gorge, at the lowest elevations, they really don't make hay piles. So places in the highest elevations, 10, 11,000 feet, in areas like here, they're massive. I mean, they're like huge. What else? What other things can I say about that? So then you have these. Some of the species that they put in those hay piles are actually. Does anyone know what lupins have in them? They have a lot of cardiac glycosides. So like can kill livestock immediately. Certain species of lupins. I've seen some pika individuals, and they're very, very unique and individualistic. Some pikas will hay nothing but lupin. Like, what are you doing? It's like that Midvale School for the Gifted, which is kind of me, pushing on the door that says pull. Okay, cardiac glycosides, that's not going to do you too well, and then, funny enough, like 100 meters away, they've taken every plant that's out there and put it under their hay pile. So, but what you see is this transition and evolution of the chemistry of those plants in that hay pile from what they bring in there, these cardiac glycosides, to becomes very, very edible over the course of the winter. So it's a really fascinating kind of like nature is amazing. Excellent question. That answer? Yeah, cool, great.
Maybe we have time for one more, if there's one more out there.
Do we have any 8-year-olds in the audience that have a question?
Oh, should I?
Yes.
So there's actually a population of pika living at Craters of the Moon National Monument and Preserve that are really interesting because it's really, really low elevation compared to their normal elevation. I was wondering if you predicted pika moving to these kind of outer ranges in the future, because I think it's really cool that they've found a way to live in lava tubes because it's so different than what they usually live in. Excellent question.
Over adult water, we'll say, later, I can tell you a story about my experience in Hell's Half Acre, which is very near Craters of the Moon. But great question. So a study was just published about pikas in Craters of the Moon versus higher elevations in Idaho. So I think first what's important to understand is that when we use the data of the regional climate, it says it's dang hot and dang dry around Arco and Craters. But then we realize, oh my goodness, it can be 15 meters thick of lava. And there's these labyrinthine, crazy fissures and stuff. And I'm like, oh yeah, I can definitely characterize that landscape. And I put out sensors and like, I was way wrong. We couldn't do anything out there. We had no idea. It was microclimate had nothing to do with it. Because I think they have available to them ice caves. They have these lava tubes. Again, you put these microclimate sensors way into the caves. It's bloody 50 degrees or 45 degrees all day long. All night long, all day long. So you have this massive decoupling of the regional climate from what they're experiencing. And so I think when we're understanding those places, those are long-term refugia. I guess the only piece that I would say is we have to be careful about what we extract from those, because those are super weird. Those are really exceptional, funky, anomalous exceptions. So that if we can somehow replicate that out on the landscape, that's helpful, useful information. But they behave so differently there. So excellent question. Yeah.